Hey guys, thanks everyone for joining us today. And today we will be talking about reactive programming, reactive systems. It's a modern approach that can help a lot of pieces of software to run faster, more resiliently, and well, it's good for every Java developer to know what reactive programming is. And today Mehret will tell us about this approach. As always, I remind you that you can ask your questions in the chats. We will try to cover them all. And if you like the light talk, subscribe to our channel and like the video to see more. And with it, I'm passing the word to you.
Okay, I think I can talk, right?
Yeah, let's start.
Okay. Yeah, my name is Mahratab. I have been working in the software industry as a professional software developer for around 8 years. Today, I'm going to present you what reactive programming is, what problems it solves. Particularly, we are going to have a demo using the Project Reactor library. So, yeah, in the reactive landscape, maybe you have come across different jargons like reactive systems, reactive programming, reactive stream API, or something like that. So let's see what reactive systems are and what reactive programming and what we are going to focus on. Reactive systems is basically related to distributed systems, and it is a systems that follow the reactive manifesto. Just a reactive manifesto describes a set of characteristics for what a distributed, a best distributed system should have. And this manifesto is created by distributed systems experts. Yeah, and this for a system to be good distributed systems, it needs to have four characteristics. It should be responsive. I mean, it should respond to requests in a timely fashion. It should be an elastic. It should scale up or scale down based on the load of the requests. It should be resilient. It should handle errors gracefully. And for this to happen, it should be message driven. If a system is based on is message driven, it can be elastic, it can be resilient, and it can be responsive. Uh, yeah. So when we come to reactive programming, it's a different concept. It is a subset of reactive systems. Maybe reactive systems can be achieved without reactive programming. But to have a better reactive systems, we can make use of the reactive programming. Reactive programming is a programming paradigm. So when we say a programming paradigm, we can think of like this. For example, in the traditional way, when we do coding, we're writing codes like, for example, do X, do Y, then do Z, something like that. But in this way of programming, we do something like that. On event X, do something. On event Y, do something. So uh, inherently it has kind a nature, it has a kind of asynchronous nature and a non-blocking nature. So reactive programming primarily provides a tool to use functional APIs. And on our today discussion, we are going to focus on the reactive programming. uh, so what was the problems that reactive programming is there to solve? Let's see the problems. Yeah, and the for example, in the we have web servers, traditional web servers. For example, we may have a Spring-based web server that is based on servlet container like Tomcat or Jetty and some other server containers. So when we have a request, what does that web server does? It allocates a thread to handle that request. Then if that request do some kind of IO operations like a call to a DB or external service or maybe some file system or something like that, the thread will be hanging there, sitting there waiting for the response to come, and then Uh, so we have that thread assigned to the request for the entire duration of the request. From the request is received by the server to the response is generated by the server. So even during the IO operation, while it will be sitting there doing nothing. So uh, we have a kind of some wastage of resources. How how do these traditional web servers handle concurrency? So when we have another requests, the traditional web servers will allocate another thread to handle that request. So as the number of requests increase, we keep assigning additional threads. So we can finally we will reach some limit, some threads in a Spring Web application. We can configure the number of threads using the Tomcat server, the max threads, but still we have a limit. So each thread process one request at a time. IO tasks can block thread execution. Thread waits for a response. If all threads are busy, requests wait in a queue. Uh, this is what happens with the traditional Spring Web server. The problem with that, and we call that approach a thread per request approach. The problem with this thread per request approach is it's not efficient. For example, every thread consumes a memory, some stack of memory, and as to increase concurrency, we increase the number of threads in the thread pool. Finally, we are going to have multiple threads in our thread pool, and this multiple threads means multiple a lot of context switches, and every context switches will consume some CPU cycles. Uh, so when we have all the threads are assigned to requests, we are going to have another requests in a queue. When the queue is full, we are going to have requests getting dropped. So in our system, finally, we are going to have timeout, something like that. A spike in external resources response time may affect dependent components. For example, uh, when external services they need to serve a lot of other requests, our request may hang out there and it may be blocked, it may be waiting. Uh, yeah, that's where the problem is with the thread per request model. Another problem with the uh, traditional way of programming is, for example, we may have a kind of function that does some tasks. For example, we have got a call to a database, then we have a call to external service, then we combine result and we return the result. The call to database is independent of the call to the service, external service. For example, let's say that the call to the database takes 500 milliseconds, and the call to the external service takes 350 milliseconds. Uh, since we are following what we call the imperative way of programming, first till we get a response from the database, we will our thread will go into the waiting state. It will hang out. It will be sitting there doing nothing. Then we get a response. It will go to the it will do the request to the external service. Then the same thing will happen. But these two things could be done in parallel. So this way of programming, which we call imperative style, by its nature, it is blocking and it's synchronous. This was another problem that we have with the old way of doing things. The third problem that we have is, for example, let's say our application do some kind of query to a database, for example, to get some list of data. And this list of data can be a huge amount of data. So maybe this list of data can be requested by many requests. So in our system may finally end up having out of memory errors. There is no way our system can slow down the database. There is no just a way that can just what do you call prevent our system from being over flooded by the response from the DB. So that's where the problem is that we have with the traditional way of accommodating concurrency and designing APIs or something like that. So what is now the best way to do things? One is to have to avoid the request per thread per request model. Another is to have asynchronous and a non-blocking approach. In the reactive model, I/O tasks are non-blocking, so the threads may process other requests while waiting for response. So what is the advantage of this approach? A spike in external resource response time doesn't block threads. They still can process other requests. You don't need many threads. So but when you have many threads, that means we have less context switches. Less context switches means that efficient use of resources like RAM and CPU. Uh, how do systems achieve this high amount of concurrency with small number of threads? Nowadays, we have what we call a concept or an abstract concept that's called event loop. Maybe I hear it first in the Node.js world, but later this concept is implemented in the Java world. And this concept basically achieves concurrency with little number of threads. The event loop have got is basically it is an infinite loop that's handled by a single thread. And this concept we have what we call events. Every request is just assumed as an event, and it will be every connection from the client, it could be read or write, will be queued in an event queue. Then the thread will go through the event queue, and at every event here will have its associated handler. Will go through the queue and or tasks, and it will just execute the tasks related to the events. If the task has got some operation like a blocking operation or equal to an IO operation, it will spin off a worker thread, and it will that worker thread will handle the will execute the handler. If there is an IO operation, it will register a callback. When the response is ready, the callback will be executed in a different thread from the thread pool. Here, threads do not block on external calls. They register callbacks. When an operation completes, it executes the callback on a thread pool. Yeah, I have already. Yeah, I've already said this one. With fewer threads, the event loop with fewer threads, it can manage multiple connections. For example, we have a NETI framework that is a network framework. It has got what we call the what we call channels, and with this channels are monitored by a single entity called selector. So yeah, and a selector can be handled with a single thread in the event loop thread. So as I have said that to improve uh, the concurrency and the problems associated with the imperative style of programming, that's the blocking and synchronous nature, we need to follow the reactive programming. Reactive programming by its nature uh, is asynchronous and non-blocking. Uh, so for we have in the market we have different libraries or frameworks that help us to do the programming in non-blocking and asynchronous nature. But for this different libraries to for example to work in interchangeably, or for example we have, let's say we have the Spring Wave Flux uses under the hood the native server and Project Reactor. For the three communicates to communicate with each other, they should have some kind of common language. So for this common language to be enforced, we have what we call reactive streams specification. they all should what do you call, implement the protocols, the interfaces specified under the Reactive Streams API. In the Reactive Streams API, we have got actually 4 interfaces, but today we are going to look 3 interfaces. The basically because we mostly use the 3 interfaces: the publisher, subscriber, and the subscription. The publisher represents a source of data. It emits events to the subscriber, and the subscriber receives events that are emitted by the publisher. And the subscription represents the relationship between the subscriber and the publisher. When we see the publisher, maybe it is clear, I don't know, in the picture, it has got only one interface. When a subscriber subscribes to the publisher, it invokes this method. Then it receives a subscription. The subscription uh, just has 2 methods: the request and the cancel. This is the way that the uh, subscriber controls the emission of the events. It can request the number of events it needs, and it can cancel its subscription. The subscriber has got around 4 methods: on subscribe, on next, on error, and on complete. When the subscriber subscribes to the publisher, it will get the subscription. I mean, on its on subscribe method, and then on next method, it will get the event. When there is an error, the event will be available on the on error method, and the when the publisher completes emitting the events, the incomplete signal will be available on the incomplete method. So for every a lot of subscribers can be subscriber to a give to one publisher. For every subscriber, there will be different subscription. So every subscriber can request a different events, or it can cancel its subscription at different times. Uh, in the market, we have different libraries or frameworks that implement the reactive stream API. We have got RX Java, we've got Vertex X, yeah, Project Reactor. Uh, Today we are going to look at Project Reactor. Reactor is the 4th generation reactive library based on the reactive streams specification for building non-blocking application on the JVM. Project Reactor is a library that implements reactive stream specification. Project Reactor and reactive stream specification are based on the observer pattern. Yeah, and Spring by default makes use of the Reactor reactive library. Doesn't mean that it is only we can use like RX Java or some other reactive library, but by default it makes use of this reactive library. So on the Project Reactor, the publisher is implemented in 2 ways: a Flux and a Mono. These are 2 types of 2 implementation of the publisher interface. The Flux represents a stream of events from 0 to n, and the Mono represents a stream of an event at most 1. So it is time to do some demo. Yeah. What I have done is now I've created a Spring Boot project. It is a Gradle project. Reactor works just with Java, with minimum Java version of 8. So today I'm working with Java 17. So I have added the Spring Reactive Wave and the Lombok in case I need it. Yeah, basically we can add another things also. Yeah, then I have already generated project structure template. In my project, I have created a set of configuration and packages. I've created the model. What in this project?
I'm sorry to interrupt you, but could you please open the presentation mode?
Okay, this one.
Presentation modes in the IntelliJ IDEA to make the
Okay,
fonts bigger.
yeah,
Yeah,
sorry.
and while you open it, I will have my 15 seconds of commercial. So I remind everyone that we have a free Java school, MJC.school, that goes from the very beginning, like how to write a main method in Java, and up to the Spring framework, build tools, CI/CD, cloud, and yeah, it's totally free. You can enroll today or tomorrow, but why wait for tomorrow? Yeah, enroll today on mjc.school. And let's proceed with the presentation.
I just need to go to the Project Explorer. I cannot do that with the presentation mode.
Oh, I think it's Alt 1. Okay.
Okay, Alt 1. Great, thanks. So in this project, I'm assuming that we have got some sensors, and the sensors they store data in some external service, and I'm going to request that external service to give me some sensor data. So to connect with the external service, we need the web client, which is a reactive HTTP client. I have configured it here, the web client. Maybe the external service is located at this URL. So uh, the remote web client, I've got a service for that remote web client. Basically, what I do is to get data from the web client. For example, to get all the sensor data, I will request at a given URI, and the web client, the Flux or Mono, we get this data sources from, for example, the web client or reactive database drivers, or maybe Kafka, reactive Kafka, yeah, drivers or message brokers. So I request at a given URI, and finally this web client, the HTTP client, gives me a flux of data or a mono of data. It can be a mono of data, but it's a mono. Mono. So, but for the for the purpose of doing the demo, I will simulate the external service call. I don't need this one. I will not need this one. I will. What I'm doing is I have created different methods. Let's assume that this methods return results from external service. So I have got a service. This service is a sensor service. It gets the sensor data by what do you call making use of the HTTP sensor HTTP client. For example, let's say that we need all the sensor data, all the sensor. I need to have a method called maybe, yeah. Let's say for the timing void get sensor data. So the service will make use of the sensor HTTP client to get all the get sensor data, get sensors data. So we have got all the sensor data. I'm just simulating the call to external services by simply returning dummy values. The sensor data is returning a flux of sensor data. So I'm going to return the sensor values. What I am doing to generate this sensor data events, I'm just using what we call flux.gist. The sensor data, I'm trying to model the sensor data uh, using this record entity. The sensor data has got a sensor ID, sensor type, and value. The sensor type can be temperature, humidity, and chemical. So get sensor data, let's assume that this is a call to external service, and that external service is returning a flux of sensor data with different values. So in our service, yeah, this is the static method to generate a flux of events. We have another also static methods to generate flux of events from array from iterable yeah, objects. So in order to make use of this sensor of data, we need to subscribe to it. Let me create a test if we are getting the what do you call the flux of sensor data. The test. Mm, for the service. Mm, I'm just only trying to work with the project reactor. I'm not dealing with the Spring annotation, something like that. Sensor service. Mm, okay. So I will test this one. Generate message test. Okay. Okay. So in order to make sure that we are getting the flux of events, we need to subscribe to that method, sensor service that subscribe. What is that? Sensor data. I mean, yeah, we need to call the first the method that gets uh, sensor data. This sensor data returns a flux of sensor data. Yeah. So in order to initiate the flow of events, we need to subscribe to that to this flux of events. Sensor data dot subscribe. The subscribe method is an overload method. First, we can handle the events. That's we have got the our next event. We can handle the events that are being published by the publisher. Maybe let's try to print out what's it's giving at. And the other is to handle if there are errors. The third one is to handle the completion signal. So let's see if we're able to generate a flux of events and where our subscription works. Okay, yeah, we are able to get all the events we found from the external service. We've got around 6 events, and here we are able to print around 6 events. Yeah, and finally we have the completed signal. If our, for example, if our service has got some errors, uh, for example, some error if some error just happen to our events, the subscriber will not get all the events. It just the publishing will be terminated. For example, let's say that when the first two events are already emitted. After the first two events are emitted, let's say that an error occurred, then the publisher will not get the rest four events. Let's say that uh, yeah, for example, let me throw an error after the first two events are published. Let's say drop map. uh, we'll talk about map later. uh, for the time being, if sensor data dot sensor type equals to uh, it's humidity, or if it's chemical, let's throw an error. Let's throw new runtime exception. Otherwise, let's return sensor data. Yeah. So after getting the first two events, we will get an error. Then we will not have the completion signal. I don't know why it's taking. Yeah, we've got the first two errors. Then we have got the first two events. Then finally we have got the error. When an error occurs, this reactive libraries or this reactive systems do not give us will not get the next. I mean, there could be, for example, some other data related with temperature. We are not able to get the last data. Because at some point in the middle, an error has occurred, and the whole the producing of events will be terminated. Uh, One thing that I want to okay, but this is not the way we do testing in the reactive world, particularly with Project Reactor. Uh, unit tests only is not enough to do the testing, because unit test is primarily purposed for synchronous and blocking. But here we have the asynchronous nature and non-blocking nature. So the what do you call the Project Reactor comes with testing all the scenarios related to to asynchronous nature of the events, the non-blocking nature of the events, the error handling nature of the reactive programming. Uh, that's all things are not we are not able to handle all those things with merely the assertion libraries that come with JUnit 5 and yeah. And by default, when we add the wave flags, the Spring Initializer gives us also the tool to test our reactive programs using the reactor test. Uh, Let me remove what I did to test an error. So to test our reactive program, we have what we call step verifier. Then we create a step verifier. That means when we pass the sensor data, the flux of sensor events, the step verifier somehow subscribes to this flux, and then we can expect the events we can assert the events we expect. Finally, we can also assert the verify complete. In our case, for example, for our case, uh, this method doesn't return an error, so we expect the complete signal to be emitted. So what do we expect from when we call this method from on the server sensor service? We expect this list of events to be emitted. Okay. Yeah, our test has passed, and we are able to verify the list of events and the complete signal. If there was an error, as I said before, let's get back to the error. If there was an error, uh, our test has to fail. Yeah, what does it? If there is an error, we only get the first two elements and not the verify signal. We get the verify error, expect error, verify error. If that is if error should happen, this is how we test our reactive code. Yeah, it has passed. Yeah. So let's get back to what the scenario without error. So the next operator that we will see on the reactive library is yeah, the map operator. There could be a scenario where we map a stream of events from some sort of events to some other sort of events. For example, in our case, from the events of sensor data, we need to get only the IDs, a string of IDs. So in this case, we need public flags as we from the data model of the sensor data, the sensor ID is a string. We need a flags of strings. Get sensor IDs. Then let me copy this one. This gives us a flux of sensor data. I need to get only the IDs from this. So what I do is I need to map it. Map is an operator that takes, yeah, this operator, we can see that what does it take? It takes a function. It takes a function, so function takes an input, one parameter and returns a value. So yeah, we need to return all the IDs, sensor data dot get sensor ID. Then we return this one. So we have mapped the flux of sensor data into a flux of string IDs. Let's test this one if it's as expected. Works. Okay, let me copy this one. Okay, I don't need this one. Okay, only this one. Dot get sensor IDs, the var sensor ID strings. Step verifier that create sensor IDs. That expect next. What should I expect? Yeah, from the I expect this IDs 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6. 0, 1. 0, 1. Oh, what is happening? 0, 1. 0, 2. 0, 3. Okay. 0, 4. 0, 5. 0, 6. Okay. I expect this values to get emitted. Then yeah. Then I should verify complete. It should complete successfully. Okay, let's run this test. Yeah. So it has mapped the flux of sensor data into the flux of string sensor IDs. The next operator that we are going to see is the filter. For example, in our sensor data, we have got different sensor type values of different sensor types. Some of them represent temperature, some of them represent humidity, some of them represent chemicals. So let's say we need only the temperature. At this time, we need to filter out the sensor data related to temperature. So let's create a method that returns a flux of sensor data at temperatures. Temperature. Sensor HTTP client dot get sensors. And here I need to filter. Filter takes a predicate. That's a sensor data and some value, some logic that returns true or false. Sensor data dot sensor type is equals to sensor type temperature. I need only the data related to temperature. Return. So we should get only the first two events, this and this one. Let's write a test method for this get temperatures method. Still sensor service that get temperatures, then step verifier that create temperatures, that expect, that expect again, then that verify complete. So as soon as we are looking for only the data related to temperature, we have only this those two values. Okay, Control V, Control V. I don't need this one. I don't need this one on the first. I don't need the second. Let's run the test. Okay, yeah, it has passed. Okay, let's see the third operator that comes with the project reactor. Let's say we have a method. As for the time being, it returns void. Get sensor by type. We pass types like an array of types, like for example, sensor type. Maybe then sensor types. And from the sensor types, let's return the. We've got sensor HTTP claim, then get sensors by type. Maybe we have yeah, get sensor by type. For example, yeah. So for each type, for each of these types, we need to return the sensor data. Let's first, if we do, for example, we can return this one from Flux that we can map. We can do map from these types to the what you call the. We have got a method that returns by what you call by type. For example, sensor types. The first one will give us some flags of sensors by type, and for the second one the same. And instead of doing this, let me create a flux. What is that? What I'm doing? I'm a bit confused here. Yeah. Let me create a flux from the array, sensor types. I do have when we see there's a flux of sensor type, but my interest is to map this type of sensor types into to get the flux of sensor data from the sensor types. Then if I do map, does it give me sensor type that then I need the what you call the list of sensor data for a given sensor type. Sensor type. So if we see this one, it is returning to me a flux of flags, but I don't want to return a flux of flags. I just return a flux of events. Map is not useful in this case. What we have is we need to flat out the inner flags into an events. So we have got a flat map. The flat map, what we have is it flattens out the internal flags. This is what I need. Return center data flags, and what I need to my return type, my method should be flags of sensor data. So let's test our code. Let's create a test for this. Get sensor by sensor type.
Let's maybe skip a test for these parts because we have few more things to show and we're running out of time.
Okay. 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 Okay, the force operator that we are going to see is, let's say we have some data, some sensor data and rooms. The HTTP client will give us a list of rooms. It gives us a list of rooms and some list of data. And the first list of sensor data correspond to each room. At this time, we need to make, for example, different HTTP calls for the first one and for the second one. Then we compose the result. The Project Reactor has got an operator to do this easily. It's called a zip operator. So let's see that. Public. Let me do void for time. Get rooms temperature. The first one is, let's say, sensor HTTP client, sensor HTTP client dot get sensors, so have the sensor data, and the second call is sensor HTTP that get rooms. We have a flux of rooms, so we can deep return. We can zip the first with the second sensor flux. We have a static method called zip. Yeah, sensors with rooms. Yeah. So let me make it clear. Okay, sensor data, and this is a rooms data. Then we can return. It's given us the tuple of the data, the sensor data. That maybe let me start the room is that. Yeah, the room itself. So let's call it this room. And it is value sensor data dot value. So what I'm doing is I'm getting the flux of sensor data and the flux of rooms. I'm zipping for each room. There is a corresponding sensor value, sensor data. So then finally this zip will take the two fluxes, and it will give me a tuple of values. And from this tuple value, I'm getting the room, which is a string, and the sensor value. So this will return a flux of string. Yeah. Then I need to return this one. Maybe we can test this one. Shall we test that?
I think no. It looks pretty simple.
Yeah. So we have seen four operators. The next operator we will see is the default if empty. For example, and the filter when we do get temperature data only, we may have, for example, let's say we have another sensor type, maybe, I don't know, chemical, humidity, temperature, I don't know, whatever, pressure. Let's say this one. we don't have any data related to the pressure. If we do this one in our filter pressure, it will, because there is no data related to the pressure, it will return an empty. At this time, there could be a default value that we may need to return. So at this time, there may be we can have default if empty, some new some sensor data. Let me copy some data from here. Okay. Let me copy this one also. So on our test, we had get temperatures. This has to fail now. What is happening here? Okay. I've added. Maybe gas pressure. I don't know. So let me the next session. Yeah. This has to fail because we don't have. It will return an empty. Yeah, it has failed. We are filtering based on the pressure sensor type. So but we are expecting two values, but now we should expect the default one. The default one is this one. Yeah, it has passed. I will. There is another to deal with some default values. For example, we have got here a stream of events that are filtered by the pressure. But if it's empty, we can default to another. Now we are only defaulting a specific single value. We can default to a stream of events, a different stream of events. It's called switch if empty. I will not show. I will jump that. Now we are going to see some operators called the do-on operators. The do-on operators.
I'm sorry, we just ran out of time. Can we probably go to the presentation?
Okay. Yeah, sorry for not using my time properly. Yes, we have seen that. So and the old way of doing web applications, particularly using the servlet-based containers, yeah, we've got the servlets in the servlet stack. We have got servlet containers. We have got Spring Security. If we are using Spring framework, and we have got Spring MVC and Spring Data Repositories. On the other side, if we are using the reactive stack, we will use either Netty, that's the default runtime environment for the Spring Wave flags, or we can use servlet containers, particularly that make use of Servlet 3.1 plus, and the Spring Security Reactive, Spring Wave flags, Spring Data Reactive repositories. These are the stacks. So when we work with this reactive programming, they have got advantages. The advantages are lower resource utilization when service makes many external calls, better resilience. Server can handle huge surge of traffic. It better handles delays in response from underlying components. And the disadvantages are debugging is painful. Actually, we ran out of time. I was about to show some debugging. Debugging is painful because stack trace is hundreds lines of long with many internal method calls, increased code complexity. Some libraries are written in blocking manner and it's not convenient to use them. Actually, we have some workaround here. We can use the sync from the reactive from the project reactor. So thank you so much. Yeah, the reactor has huge overhead. It is insufficient if you don't make any external calls and just execute CPU intensive code. Yeah, that was it on my side. We can go to the
Yeah,
question
we
and
have
answer.
only one question for now. Is this approach going to change with virtual threads that are going to be launched soon? If you guys don't know what are virtual threads, I will share a link to our video where we describe the threads in a few words.
I think they will complement as to my some study. They still with virtual threads we can make use of uh, the reactive programming. I don't think they will. Yeah, we are not going to avoid using reactive programming when virtual threads are available.
Yeah, I think that for some simple cases when you just send one request to some external service, virtual threads can replace the reactive approach. But for some more complex solutions, reactive programming provides a lot of operators for retries, login opportunities, etc. And so they're just very handy. And also, the transition to the virtual threads will take several years. Right now, the Azure cloud, one of the major clouds nowadays, it doesn't fully support Java 17. And well, maybe they will take 2 years to support Java 21. So yeah, we will spend a lot of our time with reactive programming still. Okay, I don't see any more questions, so we will be wrapping up this light talk. Thanks a lot. I think it was interesting, and see you guys next week.
Thank you so much. My pleasure.